So today I requested Jacqueline White to give an introduction to Anne Thompson. Jacqueline, of course, has worked with Anne for donkey years. Which you will see that what the donkey years are. I think it should be there. So please with that. So help me welcome Jacqueline White.
Welcome to the celebrity roast, Maniac Talk of Anne Thompson. Anne needs no introduction, a sea of friendly and familiar faces, and you've read her short description. I've known Anne since 1998, so the term donkey's years is somewhat appropriate. And in that time that I've known her, she's been my boss, my mentor, my colleague, and my friend. And over the years, we've developed mottos that not only define our time together, but also reflect the passion for the work that we do. And one of our mottos is, study ozone, see the world. When I met Anne in the late 90s, ozone had become her sexy rock star chemical tracer. And it still is today, judging by the title of her talk. Anne travels about as much as an airline steward, maybe not so much now, but back in the heyday, Anne was traveling the world, preaching the gospel of ozone like it was biblical text. Another motto that we had was, data is gold. We guard it like it was our firstborn. We covet it like it was the last box of chocolate in the universe. We would label our data disks with gold, lemonade, pen and ink, and we would joke with each other and say, did you get the gold? How much gold did you get? Get the golden run. During missions and meetings, Anne and I would play good cop, bad cop so that we could get what we needed to get for the signs that we were doing. So guess who the bad cop was, because it certainly wasn't me. Another thing to know about Anne is that she has the skills of a well-seasoned diplomat. She can talk a cat off a roof. She can make a meat lover a vegan. So a few science and non-science related things that I know about Anne that I want to share with you is one of them is her love affair of all things Africa and the tropics. A number of years ago, I don't know if you know this, but Anne did a Fulbright in South Africa, which allowed her to travel to other parts of the continent, One project that I know Anne's going to mention in her talk is that she started a project that brought me here to Goddard called Shadows, the Southern Hemisphere Additional Ozone Sondes Project. And it was to collect high-resolution profile measurements of ozone in the tropics and subtropics using ozone sonde instruments. And I think, and correct me if I'm wrong, but it was Anne Douglas who gave Anne Thompson the astute title of Ozone Sonde Queen. So if you don't know anything else about Anne, know that Anne is the queen of ozone sondes. She has a strange and ongoing obsession with crocodiles and alligators. She travels with a puppet alligator with her where she goes. There was a period where she had 1 million beanie babies. Remember the 90s, y'all? Most variations of crocodiles and alligators, and that was her Christmas gift and her birthday gift for a couple of years. I can go on and on, like her obsession with stationery and colorful pens, her collection of safari vests, how she had a tendency to eat ho-hos for breakfast at her desk at work. But I'll stop here. In this next hour, you're going to learn about Anne's dedication to her craft, Goddard and the lab, her colleagues, her friends, and her family, and her students, and how her career has been shaped by the people around her in the times. So please help me welcome Anne Thompson.
Wow, I wasn't sure how Charles Gatebi twisted my arm to do this, because I think it's a kind of thing one should do just before one retires. But I suspect it is our common interest in things tropical and African, and I'm going to, even near the end, sneak in a picture from one of the proposals that we did on this topic. So I guess that's how I got roped into it. I want to thank Jackie for that very nice introduction. Everybody's interested in like where you came from. I had a 6-year peripatetic postdoc that converted me from a physical chemist to an atmospheric scientist. So that is maybe not so typical. And I'm going to mostly go through my affair with ozone layers, first with models, data analysis, and different regimes. We are about the data from all of these sources. And I'll mention some of the projects. I'm going to end up with a little bit of, actually a fair amount of what I'm doing and what I hope to be doing, or what's next on the agenda, some exciting things. And Jackie hit the nail on the head when she mentioned the people that we work with. You can't give a talk at NASA about what you've done, about your career, without mentioning all the people that you've teamed with, or stood on their shoulders, worked with, hoped you mentored well. And what I've done is actually put their names in red in the talk, or I've used this bar at the bottom and put the students, the co-authors, and so on. And I really have to say, I didn't have enough time to do the fascinating life that I just had as a professor for 8 years. Details about the Fulbright Scholarship, all the kind of service things that I've done in ozone and climate world. But John York signed me up to talk to the Young Scientist Gathering in late June, and I think those are the people who'll be most appreciative, so I'll saving some of that for there. So this is these are just the vital statistics. I do hail originally from Pennsylvania, but I grew up in sort of equal measures of upstate New York and in North Jersey, broadly within the orbit of New York City. I did half of my public school education pre-college in each of these states and graduated from, actually, the actual high school doesn't exist anymore, but it was morphed into Chatham High School. And like John Mather, I did get to his Maniac Talk. I migrated from northern New Jersey to Swarthmore College, and he said that math was too much for him, you know, higher math. So he became a physicist, and physics and looking up to John, because he's very tall, was too much for me. So I only minored in it and majored in chemistry, and then did a master's in chemistry at Princeton. I got married at this time, and my husband and I went back to the Philadelphia area, and I finished my PhD in physical chemistry from another college that's actually a small university. George Zimmerman was really an amazing mentor. When I did become a professor, I just felt all of the training, the values, the rigor, the patience, well, he was maybe more patient than I was, came out, and it seemed to be what I was taught to do by working with George, who also actually was a Swarthmore graduate. So there's the title of my real dark lab, red lights, photochemistry dissertation. I won Woods Hole Oceanographic Institution postdoctoral fellowship in 1978. It was one of the two most important things I ever did. I guess the other one was definitely coming here. But Ali Zafirio deserves credit for taking somebody with a chemist background, a non-traditional background, and trying easily converting her into an earth scientist. And I completed the postdoc with Ralph Cicerone by going to the other oceanographic institution on the other ocean, but he took the group to NCAR. And I came here in 1984, and I will be eternally grateful. I was recruited by Marv Geller and Rich Stolarski, actually to be the lower boundary condition on all of the stratospheric models that Marv was juggling at the time. So I actually have just marked my 30th anniversary since coming here. I took an 8.5-year detour to Penn State. I just grew more NASA research. At one point, I had 10 students and postdocs working with me, and I very happily returned here in June of last year. So, who's been patient with a lot of commuting in a multi-decade marriage is Nels Larson. Next time you're at National Airport admiring the new terminal that Cesar Pelli designed, remember that Nels Larson built it. He was the construction architect on that project in the mid-90s and just completed serving a tenure as the Dulles architect with the Metropolitan Washington Airports Authority. These are my parents, and one of the things that I found absolutely heroic people to all 4 of their children. One of the things that I found interesting in listening to the talks that I came to is that we had people with long, revolutionary era roots in the U.S. And then I really enjoyed, because immigrants are my heroes, I enjoyed listening to Bill Lau and to Sasha Marshak tell their stories. Well, I'm somewhere in the middle. I'm a very typical melting pot mongrel from 2 very strong families of great family tradition, but couldn't be more diverse backgrounds. Let's see. So my parents actually both had chemical training, and that isn't why I became a chemist. I actually started out in pre-med. But they met at this, GAF stands for the General Anlin and Film Corporation. And my dad was a color and dye stuffs chemist, PhD trained at Harvard, which was a very, very long way from his town of 1,000 people, mostly of Danish forebears, in central Utah, about 100 miles south of Salt Lake City. So we span, because my father came late in his family's life and my mother came early, but they span very, very long sets of generations. So I'm guessing that this photo of my grandparents, I never met my grandfather, was taken at the turn of the last century. And these are my mother's parents, who were a prototypical Southern European immigrant family that labored through the Depression. And because of the joint sort of training and working in the same place, my parents met in this chemical lab. But I circled 3 people who, to me, exemplified this philosophy of both families, which is to get educated, to get out in the world, to do something different, to take risks, and to serve others. And it was a common theme in both families. So it was very much the philosophy of my grandmother. So these 2 grandparents never completed high school, never got to high school. But Fanny Charlotte Green Thompson, whose mother was a handcart pioneer with on the Mormon Trail in the 1850s, within 10 years of Brigham Young settling Utah, she had gone to a small college in her town, a normal school, and she made sure that her 4 children got college educations and were not diverted and waylaid to work on the farm, as so often happens in a small town like that. My other sort of hero is my grandfather. He came from a village on the island of Crete. These are their names on their passports. When they were done, they were Nicholas and Anna Varonas. That's what Ellis Island did to them. But Nico knew 6 languages. And what he was most proud of was the fact that when he was traveling around the Mediterranean about the time of the First World War, he spent some time in Alexandria, which was culturally and economically dominated by Greeks at the time, and he learned Arabic. So when he saw that his first child, who's my mother, was precocious, he lost no time in teaching her language, setting high standards, making her recite poetry in front of the other Greek families in New Brunswick, New Jersey, to her great embarrassment. But anyway, she was the pioneer who got a college education, and it inspired her 5 siblings to follow. Now, this is one of them. This is George Varonas. may be a name familiar to some of you. He's a fluid dynamicist, an oceanographer. I think he's got a current named after him. He's still active in his 80s. He's turned out over 400 people from the summer geophysical fluid dynamics program that's operated every summer at Woods Hole. He also, for many years, ran the softball operation there. George, pictured in his Navy uniform, actually didn't like the Navy, didn't like war, and doesn't like going to sea. But at a family reunion when I was not sure what to do with a chemistry PhD, it was a conversation with him that really changed my life, because he said, you know, there's chemistry in the oceans, the atmospheres, and planets, and maybe you might want to take a look at that. And so I did. So before I go into this, the postdoctoral transformation that George helped initiate, so to speak, I need to explain some ozone layers. I can't say we all live and breathe it, but we don't all just sort of live it with a passion, as Jackie said. So this is, you put up an ozone sonde. I didn't bring one today, but you get a trace and partial pressure units up to the tropopause, up through the stratosphere. Maybe you're lucky and beyond. This was taken 10 years ago, June of 2004, on our first IONS campaign when I set up the sonde program over at Howard Beltsville. And this is a humidity, temperature sounding. So these are the more conventional chemists' preferred units. For folks in the stratosphere, where 90% of the ozone layer is, and that's not what I'm going to talk about today, we've got units in parts per million, but we're down at parts per billion near the ground. Not that day, not June of this particular June day in 04, 80 parts per billion. If that lasted 8 hours, then we would be in a code red violation, and the state would know about it because they have a monitoring station at the Beltsville site. So today, all this rain, no photochemistry, maybe 30 parts per billion of ozone outside, 10 to 20 at the surface in the tropics. And then when you see a layer like this and it's really dry and it's got very high mixing ratio, you think, that came from the stratosphere. So we're very interested in the transition layer, or the tropical transition layer, or tropopause transition layer, whatever you call it, where our ozone and climate connections are of paramount interest in interactions between changing gases and climate. And then we're also interested in layers that you'll see some of that may suggest stratospheric influence in the troposphere, but also might be the advection of pollution from other places. So, crash course, simple things. What makes ozone the bad ozone? This bad ozone is volatile organic compounds, or methane for that matter, or carbon monoxide for that matter. Any hydrocarbon in the presence of nitrogen oxides with sunlight. And so that's sort of the simple thing. That's what you need to remember. And we care about ozone, not just at the surface. This isn't going to go very far, and it's not going to last very long. It won't be there, say, the next morning. But once you get above the boundary layer, the lifetime increases. And that ozone, if it's growing in time, just like methane, turns out to be a very important greenhouse gas. So from the climate point of view, I don't know, this is sort of an approximate, as I recall it, number from an IPCC, but maybe a quarter of the radiative forcing on our planet since about 1850 has been attributed to methane and tropospheric ozone. So back to what I did as a postdoc, I had to learn some of this vocabulary. This is the RV NOR. This is what took me a cruise like less than 2 months out of the postdoc in that miserable physical chemistry lab. Ollie Zafiriou had the sense to take me to blue water. I didn't know water was blue in the dead middle of the ocean. We sailed from Kwajalein to Samoa. I was hooked. I was never going to go back in that lab. But what was interesting about this cruise is that Ollie was looking at free radical reactions in surface seawater, and his hypothesis was that free radical reactions were an important source of nitric oxide, that guy that I just showed you helps make the bad ozone, that it would degas from seawater. But the only person who had an instrument that could measure low amounts of nitric oxide at the time was Mac McFarland of the NOAA Aeronomy Lab. He brought Mac on the cruise. Mac did not like sailing either. I just took to it like a true sailor. But the amazing thing is, if they were prepared for, let's say here it's a part per billion of NO today. And at that time, a place like LA would have had tens of, maybe hundreds of. This instrument was down at 1, 2, 3 parts per trillion. So it was the NO cruise. And the whole time, you know, we all have this, a good scientist just tends to doubt himself. And the whole time, Mac was going nuts, leak checking. Could this be real? But it did turn out to be a very important paper. And this means that the layer, or where we were in the ship, is probably a region of photochemical ozone destruction. And I know there's a paper just come out in ACP about a tropical ozone and OH hole in the Western Pacific by Marcus Rex and colleagues from a very recent cruise. But in fact, we had a glimmer of this more than 30 years ago. All right, so I didn't get any data. I came in with a paper about, you know, here's an interesting photochemically reactive compound. It's formaldehyde. You know, it's a pollutant, comes out of the tailpipe of the cars, but it's also a natural part of the atmosphere through the chain reactions of methane oxidation. So he sent me out, you know, with a flask and a funnel to collect rainwater in Woods Hole. That was when I'd never paid attention to meteorology. I didn't know that it always started raining at night. And I would be all kinds of places, like on docks and remote parts of town, collecting rainwater. We derivatized it and then detected the amount of formaldehyde using a UV photometer. And I even did some experiments to see what happened when that formaldehyde landed on the ocean. Actually, bacteria metabolize it. We think of formaldehyde, you pickle stuff with it, but this is one of those primitive gases, primordial ingredients in making life. And so I followed the whole biogeochemical cycle. We had a paper in Tellus, and that was sort of, I really got into atmospheric chemistry. But for the second postdoc, this is the Scripps Pier. The water's way too cold. I never went swimming in it. I decided, because I had no formal training in atmospheric chemistry, that I should do some modeling. And I went to work with Ralph Cicerone and his group, and we made a very simple 1D model. It might not even have had this many reactions in it, maybe not even, you know, a dozen, 15 chemicals. It is certainly a version of the model that Rich Stolarski and Ralph Cicerone wrote their classic, you know, halocarbons will just chew up ozone in the stratosphere. Only we took out the halocarbon reactions, although they can be important in certain conditions in the marine boundary layer. They really aren't globally that important. So I looked at how do clouds perturb radiation fields a lot, like today. You're not getting nearly the photochemistry that you would if it were sunny, and how do you best parameterize them in models. And I still was kind of working with marine atmospheres and some of the concentrations that we took on that Hui cruise. But I was just maybe settling into life in SoCal, and I couldn't believe I was California dreaming, and all the people that would just kind of barge into your office asking you for money were surfers. When Cicerone took his group, at the time I think there were 5 of us, he took us to Boulder. So when I say our modeling took on a more global perspective, these are those reactions. I don't like all some of the arrows are missing, but again, you see carbon monoxide, you see the non-methane hydrocarbons, methane. There's this important OH guy, and there's ozone. But there is important, besides this radiative effect, this forcing effect that tropospheric ozone has on climate. You know, if you change climate, you warm, you change the rates of chemical reactions. If you deplete ozone, which at this time, this was, early 80s, we didn't have the ozone hole left yet. But by the time I came to Goddard, we were putting ozone hole perturbations in some of our calculations. There's this interaction. And then, because a lot of nitrogen sources are natural, like lightning. A lot of methane sources are natural, like, there's a fancy name for it, but you know it's belching cows, it's rice paddies and all of those things. Actually sorting out the sources is still a matter of research interest to us today. But the important thing here that we started to explore is that there's lots of CO everywhere. It has lifetimes on the order of months. Methane is about 9 or 10 years. So that's everywhere. They dominate the reactions of the hydroxyl radical that only lasts for a second, but is so critical in cycling all of these other biogeochemical cycles, if you will. And so we wanted to look at past and potentially future tropospheric atmospheres and see how changes in CO and methane would affect the hydroxyl radical in ozone. So what we did was made some very simple assumptions. I don't actually know if this is, I think this is 80 or 85, I can't read it. The changes here are in percent. So we made some assumptions about what mostly pre-industrial methane would have looked like in around 1850, what CO levels might have been like. We just did that from looking at what measurements were in very clean parts of our troposphere today. It was kind of conservative. So we ran several different scenarios that are NOx dependent. You're always NOx dependent on your feedbacks in any of these environments, and came up with a sort of 20 to 30, there probably would have been 20 to 30% more OH at the time. And we looked at hydrogen peroxide. It's another oxidant. We looked at different scenarios. We looked forward in time. And we stressed the sensitivity of oxidizing capacity and also thinking ahead, but we didn't have really good tools to do it, what would be the sensitivity of air quality, if you will, to some of these changes in climate. So I guess my most cited article is this science piece in 1992. So that work was done here. And I also was interacting in this time. Here are the people that I was working with at the time. Inez Fung had a postdoc. He was playing with pre-industrial and glacial period methane sources with the GISS methane source model. She said, hey, why don't you go back and look at what oxidizing capacity would have been, or oxidants, in the last glacial max. So we made different assumptions about methane. Methane fluxes we thought we could get a pretty good handle on. And at about this time, people were just getting methane measurements, good methane measurements, back in time in ice cores. So we actually had a little bit of data. And this is from one of the papers of sort of this GISS era. The other thing that was very important, nobody pays attention to anymore, but I was working with some really clever people at EPA. They were actually the people downtown. And they were puzzling over things like the methane budget. Now this one got off the web is, this one looks a little bit more recent to me. But you can see here's the belching cows, the rice paddies. On this one, wetlands are a very small source. I'm not sure that is actually correct. We were worrying at the time, again, this is about 1990, at leaky gas transmission lines, particularly in the largest gas distribution system, which at the time was the Soviet Union. So they thought about, what if you can, control leaks? What if you change the feed of animals? You can do this. You can change what you give cows in the feedlot and change the amount of methane they produce. Suppose we have some different scenarios for methane changing other than the business as usual 1% per year, which is what we were measuring in the 1980s. So we did some of those calculations, and we saw, yeah, you could end up with lower, with more modest methane increases if you undertook some of these changes. You would not get so much bad ozone. You would have a better impact on climate. And now people have much better models, which a lot of you are working on here, You call this co-benefits. You know, if we clean up the air, we'll have a positive effect in global warming. If we get this nasty greenhouse gas that eats up ozone out of the air under the Montreal Protocol, we'll save ourselves some more greenhouse warming angst. But I'm going to come back in the very end because this problem is back with us again. So modeling was fine, but I got hooked to go back to observations in a sort of unexpected way. One of the earliest EOS interdisciplinary science teams that was selected in that very first call in the late 80s, I have to tell you, reality. This was sure payback to Peter Brewer at Woods Hole and the Monterey Bay Research Institute for all of his pushing and promoting EOS within the really visionary earth science community. So I'm back working with Ollie Z. I think Nancy Maynor was on the team, Wayne Izayas. And this is actually just a snapshot of an early coastal zone color scanner image from which you can take chlorophyll and you can wave your hands and you can get out an estimate of the amount of dimethyl sulfide that you would be getting from this chlorophyll. We had some more up-to-date oceanographic measurements and made an estimate of DMS flux, sort of extrapolating from an image from satellite. It was proof of concept. And then by having more marine measurements from other cruises like the University of Miami group, the NOAA PMEL group, we could use a photochemical model with DMS, SO2, and so on, calculate OH, and then again, if you've got the sulfur oxidated species and the DMS, you can work backwards to that flux. So we published a paper in JGR, and then this is real serendipity. The truth is, I went to the theater one night, I met a guy who was working for NOAA. He said, you know, I'm filling up one of these Soviet American ship cruises. This is a gorgeous sanitized picture. By the time I saw it, it was a rust bucket. The Soviet Union was in tatters. We witnessed on our cruise the first democratic vote ever taken by Soviet citizens, or they were previously Russians, since the 19-teens. But at any rate, 12 US scientists carting all kinds of high tech showed up on that ship with about 40 Soviet scientists who had not working equipment but were great collaborators, a crew of 80. This was floating Soviet Union, floating Russia in the very last year of its existence. But we actually did everything we set out to do, and my contribution was to work with Arnold Torres. He had one of those sensitive NO detectors like McFarland had a decade earlier, and we went out sort of, in a sense, on this cruise. I had crossed the equator, so at least I was spared a Russian-style shellback ceremony at sea. But Ollie had to be a good sport as he went through some unspeakable horrors at the equator, because we went back and forth across it. This was our leg of the cruise, and as far as what did it mean, we had all the data now to fill in all the gaps in the model, but the answer was still what Mac McFarland found in 1978. The equatorial Pacific is darn clean. And so what really was important is that I have worked several times since with the NOAA PMEL group and also the folks from Boulder who go to sea, and this really turned their idea of a ship into another platform for atmospheric research. So now they just drop trailers of high-tech goodies on the ship when they sail. And this was a big one, much bigger than the Ron Brown that I've been back on a couple times. So I was hooked back in data. As Jackie said, it really is gold. I've never lost my enthusiasm for it, and a great opportunity came along. I was starting to work a little bit with the Tom's group here, and Jack Fishman was publishing his really path-breaking papers. These are his ozone residuals, approximation of a tropospheric ozone column that he got by differencing TOMS and SAGE, or later TOMS and SBUV, and this feature just riveted everybody. Why was there so much ozone in a very, supposedly, one would think, clean part of the tropical Atlantic Ocean. And his hypothesis was it's biomass burning. This feature is strongest. It's actually year-round, which is actually turns out to be very important. But it's strongest when southern Africa is ablaze with fires like this, and that happens August, September, October. And he got the DC-8 to do the Trace A field campaign. Ken Pickering is here. He worked on this with me. A lot of other people. Donna McNamara was my research associate at the time. We were running Mark Schoberl's trajectory model, looking at where the air parcels were going. We corrected helped correct a cloud artifact in the Tom's algorithm that bleached this picture a little bit, but it didn't matter. This was, one could say, the first validation experiment that we did in kind of a modern era, and we nailed it. It really was mostly biomass burning, although greatly helped by the fact that there's subsidence over this part of the ocean practically all of the time. We tested our photochemical theory. A lot of the NO in the free troposphere was from lightning. We could see that, measure that on the DC-8. But besides this sort of easterly source and recirculation in the South Atlantic Gyre, what I was most interested, because I've been working with Tao, with Joanne Simpson, the cloud resolving model, and with Ken, who was doing sort of the heavy lifting on this work, was we thought that if you were burning on this continent and you were getting into the early part of the convective season, you would pump ozone, not soluble, the ozone precursors that I showed you, a lot of those hydrocarbons, CO, NO, into the upper troposphere. And it has a longer lifetime there, and it would continue to react as air parcels moved over this region. So this is where I got hooked on SON data. These are Natal, Brazil soundings. There's Natal. These are a couple days apart. Ken was on a DC-8 flight in here that is in a kind of a highly cited paper of his. When he combined the measurements, ran photochemical model, he calculated up to 15, 20, maybe 30 parts per billion per day of ozone forming from those recirculated pollutants, but also from the lightning. And there's exactly what we observed in a couple of these ozone SONs 2 days apart. If you looked at the 100 ozone SONs that were collected at 5 sites that Fishman put together, they're noted here by stars. There's one actually missing here, but this is Irene, this is South Africa, this is Brazzaville, Ascension Island, Star, and Natal. You could actually come out with an ozone budget that said about a third of Jack's Max was from South American burning, and about 2/3 was from Africa. So that actually ultimately led to the Shadows project, because for process studies you can't beat the information, the resolution that you get from SONs. And also there was a lasting impact of this activity that included a lot of people from Africa and Europe in the Safari 2000 that Michael King put together for Terra validation, and ultimately I had a lot of visits every year, every couple of years back to Africa. Jackie alluded to that. I did have a Fulbright and spent 8 months there in 2010 and 11. So what have I been doing since the Safari 2000? Well, I talked a lot about shadows when I gave a lab 610AT seminar in August. And the important thing is that this has been an amazing data project. It was a 3-year funding. I'm really happy to say that Mike Carrillo's here. A lot of the support through the years has come from him and from his successors, but it's brought in a community of people who want these data for satellite validation. But if you hang around 15 years, you can bet people are going to start mining it for trends, so I'll show you a few of those. But if they want to use it for trends, especially in the lower stratosphere, they keep putting higher and higher requirements of accuracy and precision on it. So a lot of my time and a lot of why I came back here was to be able to devote full project attention to quality assurance, to reprocessing data, to working with the global ozone sun community on standards. And we have supported more than 10 satellites in the last decade. So I was skeptical of some trends when I gave the talk last August, but I'll show you some that I really believe in a few minutes. The other thing that I've been doing in the Tropospheric Chemistry Program, TCP, for the INTEX, the ARCTAS, and most recently for Seekers, is then coordinating networks like this one. This was ArcIons for ARCTAS, where you get everybody coordinated to put up sondes every day. The frequency in a network like this is only every week or every couple weeks. That's all you need. But if you want to look at processes on the short time scale that the planes are operating in, you have to put things together more quickly. And thanks to Jackie, she's been the archiver for all of these data. People love them. The 2006 campaign was the first one that was used to validate the instruments on Aura. And the last thing that I've been doing, which is one of those things that mushroomed or I couldn't have anticipated when I went to Penn State, is I was really excited to be part of one of the first EV suborbitals. We have one more deployment. It's Jim Crawford is the PI at NASA Langley. He is he's a taskmaster, but a joy, a diplomat, and full of energy. And he's got the P3, the U-200, which the Scott Jantz's instrument is on. And we just take this kind of pattern. You get into the P3, and I like to fly in that plane. That's real flying. And yet you like this, because you spiral, and you spiral, and you spiral, and you only go a few miles. This is Beltsville. This is Washington, Baltimore. The pollution capital of Maryland is a very pristine place called Edgewood. It's an Aberdeen proving ground. This is MDE's trailer that tells you how dirty it is. Why? Because there's a little microclimate, and the air goes over the Chesapeake, kind of cooks, and then Bay Breeze shoots it back in. And it is the bad boy of ozone between Washington and Philadelphia. So we studied that. We've gotten, I think to me this has been a real paradigm shifter. By getting all of these statistics, you see what your requirements will be for geostationary viewing, but you also learn something about processes. There have been at least 20 papers that have come out of my group, out of the Howard Beltsville people, out of the University of Maryland group with Russ Dickerson, that really have answered some long unresolved questions about the scales of pollution in this region. So this was wintertime particles, not so exciting for ozone people. Houston, we were there last September with Seekers. I'll show you some results. And we're all geared up to take native, and I will be working with, these are my students, Ryan Stauffer, Hannah Halliday. We'll be going out to Denver this summer. So this was my last slide, I think, from the August talk. And these are the satellites that we've been supporting with shadows in the past sort of decade. But I wanted to show you a little bit what's new since then. I'm excited because, when I went to sea with NOAA in 1999 on the Aerosols cruise, we found a tropical Atlantic paradox. It's related to Jack Fishman's feature. It turns out that when it's not burning, there's still more ozone in the South Tropical Atlantic than there is north of the ITCZ. So I've got a new paradox, which I've been working on. This came out of our Fulbright work, and the one student who came to South Africa for a couple short visits, Nikolai Balashov. So he just had a paper in JGR, and what we're looking at here is, here's South Africa, it's this big country, and we're zooming in on the area. How many of you are familiar with that NO2 Omi Skiamachi hotspot? That's in southern Africa because these are the power plants that drive all of the electricity, all of the economy, and all of the really ability to exist in southern Africa. So scattered among these big power plants are some monitoring stations that have operated since 1990. And it turns out they don't have data sharing policy the way we do. And it was it was part of my shock in actually trying to work there, was what it took to get a few years of data from 5 stations. And this was quality assured. Nikolai was very exacting about it. And what he found was that the variability from 1990 to 2007 was almost entirely, there's a connection between the ozone and the NOx, but the variability year to year was almost completely driven by the El Nino. Not necessarily the pollution. And part of the reason is that this is sort of semi-rural. This is probably like going to Edgewood, Maryland. This isn't really right smack in the mega city. This is the mega city. This is a picture I took in May of 2011. I was driving in Johannesburg past one of those townships where people, it was cold. It's cold in the Highveld. I've never been so cold in my life. They don't have heat. They don't have central heat. These people are living in shacks. The only way they can keep warm is by burning charcoal, burning kerosene, anything they can get their hands on. And I was in a cloudless blue sky, and all of a sudden I'm looking at this, and I thought, oh, I'm going to be breathing this for the next 2 weeks, and I wasn't. By the time I got to the other side of Johannesburg, as I got up toward Pretoria, it cleared up again. But this is a lot of what developing megacities deal with. So an El Nino signature, but no trends. These are the trends from the 5 stations that Nikolai looked at. The details are in this paper. So no trends in this period. Now, we took trace A period ozone sonde data. So 1990 through 2007, same period the Balashov took, and we had some missing years in there. We patched it in with the Mosaic aircraft data, that was the planes, the commercial planes that were coming into Johannesburg. So we got continuous data for this 18-year period, and that which is hatched, which is this green and yellow, is the only place there was a statistically significant trend. Now, we had some sampling artifacts in the SONS, because I kept telling should have thought of this. I kept telling the people at the South African Weather Service, well, we're moving, our satellites are coming over about 1 o'clock in the afternoon, so how about you move your launch time? Well, by moving into the middle of the day when the boundary layer was full of pollution versus launching at 8 o'clock in the morning, which is what they were doing in 1990, some of this might be artifact of sampling, but we have eliminated the boundary layer. This is 4 to 11 kilometers. Couple things of note. No trends in the biomass burning season. I mean, this is where we've focused all of our field efforts. Nothing happening, no change. But in the late fall and early winter, 20 to 30% per decade changes here in the free troposphere. Only really concentrated in the winter, and then almost disconnected from this feature in the upper free trope, up to 30% per decade increase. Now, this feature we've been able to explain. We're getting toward, TTL. This might be a dynamical feature. There doesn't seem to be a way to get around interpreting these as some kind of change in the transport of pollution into this region. Now, let's go to Réunion Island, one of the shadow stations. This is the one. Here's Irene, by the way, South Africa. This is just to the east of Madagascar. They started SONS 6 years before shadows, so we have a record from 92 to 2011. Again, what's hatched is statistically significant. Little trends here in the summer. In the winter, in a much more isolated period and in a more isolated region between about 6 and 13 kilometers, 50% per decade increase in free tropospheric ozone. I mean, that's kind of amazing for people. And I've been there, that's really, if it's a clean tropical island, or so you think. But this is what's going on above. And I've shown this to a lot of the modelers here, so I'm trying to learn more about emissions. People are looking at their CTM output. I think fire emissions, seasonality, but again, if I come back to that prior picture with that smoky place, what actually are the emissions in emerging mega cities? So I don't really have data to look at this. I'll be scratching my head over it for a while and bothering more of you to let's go back and look at models. Again, nothing going on in the biomass burning season. But Jackie ran some back trajectories for this region, free upper trope. And so These are the ending points, 5 days. This is, so if you looked at Irene, you're kind of looking at this region. You're looking at Africa, this region where the ozone always sits, any time of year, spring, fall, winter, summer, you've always got ozone here, so some of that contributes. But a lot of these trajectories are back in that region that we were curious about in 1992 in Trace A, Eastern South America, which is now loaded with mega cities. 23 million people in Sao Paulo. I don't know what they're putting out, but it seems to me it might be worth checking out. And the other thing about La Niña, if you follow this back a little bit further, in fact, some of these trajectories are not just from the west. They go all the way back towards Southeast Asia, places like Indonesia, Kuala Lumpur. You can get those dirty air pictures in either of those places as well. So I'm wondering if we don't have sort of what I call bellwether for long-range transport of southern hemisphere pollution that we might not have thought about before. So I'm back again, more pictures. This was in Nairobi during my 2011 visit. This is like driving the Beltway. This is a fancy, easy tag kind of highway to the airport in Johannesburg, and I'm driving. Nikolai was coming in for one of his short trips, and I'm driving along. It just like right there's the flames. They're just torch, 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 torch. Again, this is May, the month of May. So all of these sources are together. They're very much part of land use change as the migration from the rural areas which we focused on in campaigns, and that type of savanna burning is now migrating to cities, creating all over the world places like that. Our geostationary satellites aren't going to see into tropical and subtropical megacities, certainly not in the southern hemisphere. So this is my slide. I'm not going to the Ames meeting next week, by the way, so this is a slide that I'm going to send to Danielle Jacob. This is what we need to do. I think we need to go out there and do something a la Discover. Actually just drill down and look at a prototype city or two to understand something about the sources. I think there's no other way we can do it because large-scale models and inverse approaches won't be able to get a handle on it, and the sources are amazingly complex. So that's probably why Charles invited me today. I want to show you something else I'm working on right now. I said stay tuned about seekers, so I showed it this at the science team meeting a couple of weeks ago. So this is an ozone sonde curtain up to the tropopause, the ozonopause anyway, is a sort of red-brown transition zone. This is Seekers. This is a period of overlap with Discover, and then Seekers went home around the 20th, 23rd, left Discover in its own, and Discover waited and waited and waited from the 2nd until the 25th of September to get one pollution episode from Houston, which is the ozone capital of the U.S. Bottom line of Discover AQ, we really have cleaned up the air in this country. It's a good thing. But anyway, just before this, we had one of these, I suspected, stratospheric intrusion episodes. We could actually look at the P3 data and confirm that the CO went down, the ozone went up, we had very dry layers. And then there was also one of these stratospheric intrusions early on in Seekers, the 19th of August. So I've been working, this is Brian's not here, he's at headquarters today, but he's hooked me up with Leslie Ott and Andrea and Eric over running a high-res model with tracers, stratospheric tracers injected above the tropopause sort of every week, and you can follow that air. And you actually can capture some of the features that you're suspicious of in the ozone sondes. And so I've got an example. This is from that, these are sondes from the native trailer at Smith Point. We were just to the east of Houston, but it's Smith Point, it's central Houston, and it's Ellington, that sondes from all of those sources on the prior curtain. And this is how we plot them to look for these laminae, a method that I've developed with my students at Penn State. It was suggested to me by Brad Pierce. So P3 is only going to get up to about here. But you can see amazing layers, really clean background over Houston, 30, 40 parts per billion. pretty clean, but these laminae are identified by this method that we borrowed from Teitelbaum's formalism as having some stratospheric origins. That's our suspicion. So we can confirm this with P3 tracers, but we don't have any aircraft data on this date above that. So here is what we get from this tracer of stratospheric influence. It's a cut at 95 west, so that's a longitude through Houston. This dotted line is the latitude. So this is like looking north. This is the upper Midwest, and if you come down here between about 5, 6, 7, 800 hectopascals, 30, 40, 50, 60% influence on the ozone from the stratosphere. So we're pretty excited about this, and we found features like this in our Discover data for Maryland and in some other Seekers and Discover 2013 episodes. So we're continuing this analysis. We actually have a proposal pending on that. So what's next? I got to finish those studies. Got to go to Colorado with a native trailer. I'm going to be bugging a lot of you to try to figure out what's going on with this new ozone paradox. For shadows aficionados, why did I come back to keep that data coming? And we had 5 stations sort of get gaps for various reasons: equipment, funding, mostly personnel. Somebody retires, there's nobody with the dedication to carry on the measurements. But we've got 4 of those 5 stations back online, and I'm working on Ascension. And believe me, I'm working on Ascension. I'm not going to let it go. But I've got to show you what I'm doing with ACAS, because I got these results on Monday from Deborah Collinage, who's the postdoc that works with me over at ESSIC. So this project, partners, we got a little bit of Tiger Team funding, like a one-shot infusion of money to see if we can use satellite data to learn something about oil and gas extraction as sources of pollution, and particularly methane. I told you I'd bring you back to the methane story. This wasn't on the radar screen when we did those studies 20, 30 years ago, that we'd be fracking the hell out of the entire planet, so to speak. We're not the only ones doing it. And so what air quality managers want to know, and you've got to give them products that they can use. You can't say, I'm doing a study, I'll write a paper. No, that's not good enough. They want to see something with their eyes. It's a believable piece of satellite data. So where are these regions, and who are the stakeholders? Maryland Department of the Environment wants to blame Pennsylvania. Pennsylvania is not interested, as far as I can tell, because they're in, this is their new coal. They're riding high. But we're downwind. We get an air quality violation, and we blame them. We prove it. We don't get a fine. So that's Marcellus. This is called the Bakken. This is unbelievably dramatic because there's nothing else in North Dakota. It's got the most booming economy in the country right now because of this type of activity. It's called the Bakken Shale. There are a lot of shale gas and conventional extraction going on throughout the 4-state region of Wyoming, Colorado, Utah, New Mexico, and so this is actually where I'm going to focus my efforts. The heck with ozone. I don't think it's going to be very exciting in Denver this summer. Maybe. I hope I'm wrong. But if not, we're putting native in the middle of feedlots and fracking. And boy, do they frack. It's the first time I actually saw the operations. These trucks go all day and all night. Guys walking along the road with a gas mask. I'm going to put up ozone balloons, of course, and tell them I'm doing a little ozone experiment. I'm not going to tell them what's really in the trailer, which is, PTRMS sniffing all kinds of hydrocarbons. And actually, the picture I'm going to show you relates to this area, which is where we did Discover in January of last year. And so Deborah said, I went to the Central State Air Quality Managers meeting, and Brad Pierce, that I was working with, is really skeptical that we could do anything with, this is TESS data. TESS isn't doing global observations, but now it does these nice obs while we're in the field, and it can't see the surface. This is the P3 data. Native was here in Porterville. This place is the most polluted, disgusting place I've ever seen in the United States. This region where it's 2 pp M from the satellite, so that's free trope. You get more than that near the surface. This is the P3 data. I've never seen anything like it. And the little town north of Bakersfield is called Oildale. So there's a lot of particles, there's agribusiness, there's all kinds of extraction activities. But it looks like it's for real. And I think people are now, if we can connect our aircraft measurements to this kind of satellite data, they're going to believe. The wow picture that was unbelievable, I didn't want to show it. Brad Pierce is working on this Bakken, North Dakota. He's looking at oil and gas flares with a Veers product, and he can see individual flares. And he got one of them like off the charts. It's at the top. It's beyond. It just popped the algorithm, and he can drill down in that location, and you can see it, with GPS, and you can zoom in, and you can see the operation, and you can see an aerial photograph, and you could go and find somebody if you didn't think that was a good thing to do. That's up to the state of North Dakota. But anyway, pretty powerful. So those are my adventures in ozone layers, a few digressions into methane, and I owe some very special thanks. I never dreamt several years ago that I'd be here today back at NASA, and I really want to thank these people who, many of them are in travel today, who are very aligned and willing to, eager to welcome me back. I'm very grateful to them. I am working with the Wallops group, Walt Peterson, who's, you heard him do GPM validation. He's an amazing guy. And all of this was made possible by the UARP support. My last version, 1.0, people that sort of kept me going, mentored me, were very appreciative, were those that I've pointed out here, those that recruited me. Franco played a big role. Mark gave me just a million pieces of good advice. Newman in a special way, the same thing. These are my kind of my senior women support system, and it's really very sad that Joanne Simpson, who has been very, very good to a lot of us, is no longer with us. But in the end, it's dollars, and I really, really want to thank the people who have made all the things that I showed you possible through the years. It really has been the same funding stream and the same mission while I was at Penn State. Bob Watson, he's now Sir Bob, incredibly visionary, gave a lot to everybody in the ozone group, so to speak, and other people at headquarters. This one, you kind of have to laugh about if you ever knew Joe McNeil. But since he left, there have been a series of rotators who've been doing a great job at TCP, and some of my other cronies and those who kept me going. 16 students, 15 postgraduate degrees at Penn State while I was there. And I'll stop.
I think we'll take one question for Anne, and then we'll edit there. So quick comment, question for Anne.
I'm around. If you can figure out some of those ozone puzzles, come and see me.
Yeah.
If you want to advocate for the same things in future missions, come and see me.
Okay, if not, so let's give her one final thanks.